Now, who's sticking around?
What do you mean by sticking around?
Yeah, somebody told somebody to stick around.
I mean, I can leave if you want.
You're on thin ice, Jordan. Don't tempt me. Okay. So it's 2 minutes prior to class, but why don't we get started with questions?
Yeah,
Yeah,
so
go ahead, Jordan.
can we see the output for P, what is it, P2 now? Can we see what it does when you feed 0 to it?
Okay, so 0, yeah, let's find out. Because you can't type in a -0 to remove it.
Yeah.
So let's see if I have it here. I'm not projecting. I know, I understand. I'm just looking for the program. What is this? Oh, here it is. Okay, and is this? Nope, that's not what that is. So let me just try building something, and then I'll be able to project it. Yeah, okay, ready to go. Okay, so here's the program. 20:0:30. Okay, well, I guess you can put in a 0, but is there any way to remove it? Nope. Okay, so 0 can go in, but it can't come out. Sort of like a Roach Motel.
All right, makes sense.
Can I ask my question?
Yeah, go ahead.
Within within ARM, how do we do something like an AND within an if statement, like if X and X is true?
If say it again.
How do we get an AND statement within ARM? Like
Okay,
if X and Y is true.
that's pretty cool because you'll get a chance to see what it is that compilers do for you. Okay, so if you were to write if A and B code. Okay, so this is what you're asking about, right? And A and B could be more complicated.
In ARM, but yeah, more or less.
Yeah, right. So I'm just making sure I got the right stage. So of course, A and B can be far more complicated, but it still comes down to a Boolean, right? So I'll just use this. So if A will take to mean if A is non-zero, and B is not 0. So do the code. So this is a beautiful, concise syntax, and the compiler is going to build for you code such as the following, and I'll just do it in English first. So test A, and if not A, go to end, then the only way to get here is to testing B is if A was true. If not B, go to end.
So we would basically have an if-then statement followed by another if, which the first one point lets you continue, the second one also lets you continue.
Mm-hmm.
Okay.
Yes. So and then if that's true, then code, and then end. Okay, so if you remember when you were introduced to and or, you learned that from left to right, if you have conjunctions of and, the first time any of them fail, you don't have to check the rest, right? So if A was false, then B would not even be tested. True?
Mhm.
Okay, now look at what I wrote here, and you see how that works. So if A is false, you don't even get to testing B. Okay, so Thomas, does that answer your question?
Yes. Yes, it did.
Awesome. Okay. All right. How may I answer questions from other people? Because our first thing is always review.
So I have a couple of quick questions. So when you call a function, registers 0 through 8 are white. Does that also mean that functions can't call like the X9 or over registers? Like they can't like use them as use them at all?
No. So X, the 0 through 7 are never expected to be preserved by a function call. Okay? If you want to use 8 through, what is it, 18, I believe, 8 through 18, if is the same thing. That if you want them to survive calling a function, then you have to store them on the stack and then taking them back out. Okay, so in both these cases, if you want them to survive a function call, you must do one of two things. You must save them by A, push on stack. So you're saving them in memory. Or B, put into 19 through 29, and don't use 29 either. And of course, you can't use 30.
28 would probably work better than 29.
Yeah, okay. I'll buy that. All right. Now, what about 19 through 30, which is appropriate in this case? If you're going to use 19 through 30, then you have to back them up, because you can assume that any function you call will, if they use them, will back them up, so that when they come back to you, when they return to your code, X19 through 30 is put back where it was. Okay, actually not 30, forget about 30.
All right, cool. And then for my second question, so whenever we're doing function calls, we always increment X30 by the stack by 16, and then we store where that is in X30.
Mm-hmm.
So let's say in the main function, you store something on the stack, 100, well, I guess, some multiple of 16 away from where the stack pointer originally is. Does that mean now when you're in a function, because it's been incremented by 16, that you basically take whatever that initial displacement was and then like decrease it by 16? Did I explain that well?
No.
Okay, yeah, that's what I was, yeah, I feel that like it's a picture thing I need to show.
Yeah.
Isn't the SP relative to the function you're currently in? Don't like when you're inside a function, it has a frame pointer, I guess. Is that what it is? Where it's relative to that. So
So the frame pointer starts at the frame pointer, it gets the value of where the stack starts for your function relative to that function. Then within a function, you could add more local variables. In other words, put more stuff on the stack, but the frame pointer stays put. But that wasn't Joshua's question.
Yeah, am I able to like share like a MS Paint thing real quick to like explain?
You tell me. Let me make you shareable. Okay, go ahead.
I gotta mute myself. All right, so I'm assuming I'm sharing the screen.
Mhm.
So, okay, so you have your stack, you have negative, plus. So you have your initial stack pointer here. So when you're in main, it points to here, and then I call some function, right? And so I have to do the -16 things. Now it's pointing to here. Let's say in main, I at like 64, I store something 64 away. So I have some variable right here. If I wanted to access that variable while I'm in the function, does that mean I only have to do, I don't have to go 64 away anymore. I just have to go the 48. Is that correct?
You've got something there in your concept, but there's a little bit of things going wrong in the picture. Allow me to draw. Yeah, okay. Here. So here's the stack like you had. Now, conventionally, address 0 is here. So the low addresses are drawn at the top, but that's just convention. So, okay. So suppose in main, the stack pointer is here. That means that main's local variables are here, not the other side. So let's say main allocated a 64-byte array as a local variable. So relative to main's stack pointer, that's going to be some positive offset from the stack pointer to get to that array. And now main calls foo. So foo would be, let's get a different color. So when you're in foo, the stack pointer is still here. I'm sorry, the stack pointer is there. Notice main stack pointer is still there where it was. So foo's local variables are here. And in case your part of your question was, if I'm in foo, can I get at main's stack? Was that your question?
Yeah.
And how? So the answer is yes, but you ought not to do that. Okay. So the answer is yes. And because all it would be is to get to main's stack, foo would be SP with an offset of, greater than, this is not real syntax, greater than foo's stack size. Because here is foo stack, and if you offset by a positive number bigger than foo's own stack, well, then you're into main stack. And you may think, oh, that's a real fast way of passing variables without actually passing them. Well, yeah, but it's non-standard, and B, nothing tastes quite as sweet as a crash that you get by messing up your stack. Okay.
Isn't this generally what you should use the heap for? If you want to access data across things or globals, I guess.
Yes, you you should avoid reaching into someone else's stack frame. Yeah, it's just it's a recipe for tears. Okay. Okay, so that was your question, Joshua.
Yes, it was.
Okay, we're batting 1,000 so far. Another question, please. Okay, well, I have an agenda, and at the end of this other material, the new knowledge, we will take project questions. Okay. All right. Now let me clean up. Well, I don't want to spend too much time cleaning up. All right, that's good enough to start. Okay. Now in project 2, you have a struct. You have a struct called node, and the struct contents is node star, and then a int payload. Okay. Now, whenever a struct is allocated, it's just a malloc, like any other malloc, of some size. So one of the first things you'll want to note about this struct is, what is its size? And I know Thomas can tell me.
Its size is 12. However, if you use the my size thing in C, it will tell you it's 16.
Right, so which one do you believe?
I believe the 16 because that's the size the system is telling me.
Right, so if you were to do the keyword, which is interesting, size of is unique as a keyword because it's a keyword that requires parentheses. So size of node, the answer is 16. But let's inspect node. There's an address. So I know that addresses are 8 bytes. So this is the node star, and I know that that is 8 bytes. And then there's an int, which I know is 4 bytes. And that would be payload, and that is a total of 4 bytes. So 8 and 4 is 12. Yet the size of this is 16. So in reality, there are 4 more bytes here, which are in memory, but you don't have a member variable for it. Okay. And before Joshua asks, yes, you can get at those 4 bytes. Okay. So the question is why? Why waste 4 bytes here? And
Doesn't
ahead.
it have something to do with how it always wants to deal with it in valuables of 8? Because
You're partially correct. Yes.
It
So
could
it
be
depends.
because, is it because the node is size 8? Or the node pointer is size 8 before it?
Well, the struct, to begin the struct, it's going to want to be on the natural alignment. So here's this concept of natural alignment. So addresses are 8 bytes. They want to start on an address, which is divisible by 8. Okay. And an int wants to start on an address divisible by 4. And a short wants to start on an address divisible by 2. And a byte can start anywhere. Okay. So I'll tell you what, let's start writing, and I'd like you to write this also. Let's start writing some experiments and see what's what. Let me switch over to my ARM machine, and I get to demonstrate once again my VI foo. So alignment. All right. So dot text, and that says this is where the code is coming from. Code is going to be entered. Dot align 2, because code has to start on an even address, and dot global for name. And here's name. I should have done this before. STP. Let's assume I'm going to use a register. I don't know why yet, but let's just assume it. X30, and let's just do this while we're here. So I want you doing this with me. And just to make it neat, I'll
Professor, don't you want to have the move at the LDP at the end? Well, before the return.
the LDP is before the return.
Yeah, probably just thinking of something dumb because of the MOV that you have in front of it, or behind it.
Mm-hmm. Yeah, well, notice the MOV has no impact on anything except W0. Okay. Now, let's define, I'm not really running Vim, am I? Okay, so let's define a struct. Let's take the struct that we have. So just for, I'll put it in the comments so that you can see it. And here is a node star and a int. Close the struct. Okay. So now I need one.
So isn't there supposed to be a semicolon at the end of the closing parenthesis for structs?
Yeah, there is, but I'm not really writing C code, am I? It's a comment.
I know.
Yeah. And now that I've done this, I realize that, holy cow, I didn't want to be in assembly language. So I'll hold this. I'll hold this, but let's go into C for C++. Sorry. It was fun though, wasn't it? alignment.cpp. Okay. So now I really do need to write it. Okay. And
So I have a quick question. So
Go ahead.
on project 2, you said it's an unsigned int. Do you want us to? So do you want us to basically just treat it as a? I mean, you're writing it as int here. Is that just for the purpose of the instruction, or?
yeah, it's just for the
Okay.
purpose of the lesson.
Okay. never mind.
Okay. So check this out. Why don't we find out what the address of n is? N is the node. So I want to print this in hex. And so n is at 0x and the address of n. Okay, I mean, that's good enough for now. I need a using, don't I? Okay, write that. Now GPP and alignment dot CPP. Gosh, that takes a long time.
You're using VI.
I mentioned this earlier.
Okay. So that's the location of n. Also notice it's a very high, a very big number because it's on the stack. And the stack is where? At very high memory. Okay, but thinking of that address as a number, let's demonstrate that the offset of the next member next, is 0 bytes away from the start of the struct. So let's demonstrate that. So in essence, now this first time I'm going to do it, it's going to be wrong. Let's see what happens. So what I want is, I'm still in hex. So offset of next relative to n. So that's what I'm after. And let's see there. And oh, I don't know. Let's take n dot next minus n. Is that going to work?
Probably not. Because you're
Yeah,
not getting their address, because that won't
Right.
access their address.
Right. Yeah, this is like totally wrong. Let's demonstrate.
I'm surprised G++ let that compile.
Yeah, I'm surprised too. But the answer is wrong.
Did you? No, never.
Oh,
You
wait.
might not have saved.
Yeah, let me see. That it compiled because I didn't actually save it. Let's try that again. Okay, yeah, that didn't compile. It helps if you save it.
G++
All right, so-
is really slow on this computer, virtual computer.
Yeah, it's a virtual computer. Maybe to save time, I could shift over to a real computer. But I'm going to keep going. So, all right, well, that didn't work. What I really want to compare is the addresses, right? So I know how to take an address, put an ampersand. I put an ampersand, so I want to compare the address of that to the address of this. All right, let's try that. Does that work? That doesn't work either. All right, I got an idea. Let's convert everything to void stars.
Oh, wait,
How's that?
Professor,
Yeah,
you're supposed to be using, I think, n dash next, or dash greater than, because you're trying to access a pointer, or no, that's not right.
No, I think you should not use ampersand for dot next, because that is a pointer.
right. So I'm trying to do pointer arithmetic. I want to compare the, I want to compare the address of next to n itself. And I'm going through a process.
Next is already a pointer. Next already has the, this is like pointer, that's star star, not just.
Yes, Cephas, that's exactly what I want. I want to know the address of the next member of n. So yes, it's true that next is a pointer, so the address of next is a pointer to a pointer.
Okay.
All right, so okay, I'm still looking for addresses. Remind me not to do this again. Okay, so will this work? All right, let me try that. And let's see if that works. Okay, well, you can't do address arithmetic on void stars. All right, I have a solution.
Cast it to a char star.
Exactly. Okay, let's try that. And now I think it'll work, and I think it will give us a value of 0. Okay. So if you have the address of n, then the way to get at n next is with an offset of 0 or no offset at all. All right, let's go back and then add 2yy. So how about the address of payload relative to n? Let's put that in there. All right. Okay. So this all makes sense now, right? If you want to get at the value of payload, you can find it 8 bytes after the start of the struct. Okay, now let's take a look at, let's add another printout. And that will be let's also take a look at the size of the node. And let's confirm that it's 16 instead of what you might expect of being 12. And I should get ready to do this on the Mac so that it's faster.
Macs are really nice.
Well, native machine in this case. So just new file, and I'll just copy what's here, and then just sweep it out. Copy, paste, and just save this. And okay. And of course, now I'm wondering, G++, I have G++, yes, okay. So I'm going to switch to the Macintosh. Okay, everybody see that? The Visual Studio Code. Okay, so G++ alignment. Hello?
We hear you.
Where the hell did I just save that?
You're in PK
Oh,
negative
I'm in-
numbers,
Yeah,
not
I'm in,
VS Code.
I committed a common problem, a common bug. Let's move that out. It was in the VS Code directory. So G++ alignment and okay, so the size is 16. So we verified that unexpectedly the size is 16.
That was so much faster than the other one.
Yeah, so it's worth skipping. All right, now let's tell you what. Let's add another int and call it second int. Ugh, spaces. I hate spaces. Okay, so let's look at the offset of second int. And second int. Now, where do you expect this one to be?
After payload.
Should be an offset of 12 off of n.
Okay, offset of 12. And what do you think the total size of the struct is?
16.
16.
I added a field though, guys.
Oh.
Oh,
Oh,
Yeah.
he's tricking you. Ignore
It's
him.
still 16 because 8 plus 4 plus 4 is 16.
Right. Okay. Good one, Thomas. Good one,
42.
Cephas. You know, let me digress. When I was a child, I both worked and played at a resort in the Catskill Mountains, upstate New York. And in the neighboring resort, there was a person who was extremely mentally impaired. And I'm getting to the punchline, but the only thing that he would say is 42. So he's like Hodor in Game of Thrones, but all he said is 42. Now think about that.
He was the answer to everything.
Yes. All he would say is 42 and burp. He also burped. Okay, so 42, just like that.
So you're telling me you were this close to greatness for discovering this person, the answer to the life, universe, and everything, and you didn't do anything.
This is in like 1966, 1967. Douglas Adams had not written those books yet. He didn't write it. But all Moish said was 42, 22, 22. Just all day long. Okay, interesting. All right, where was I? So I want to see what the size is. So Cephas says, I'm tricking you. And I was tricking you. The size is still.
The size is C.
Yep, but so tell you what, let's go C out to decimal. And do that again. Okay, so the size is still 16. Okay, no problem. How about all we're going to do is we're going to have the same three fields, the same three, but I'm just going to put the int over there. Okay. Of course, that's going to change the alignments. It's going to change the offsets, I meant to say. But will it be changed in the way that you expect? It's the same three fields, but now the length of the node is, size of the node is 24. So second int starts at offset 0. You expect that. And then next, instead of starting at 4, it starts at 8. Right? Why? Because a pointer on this machine is 64 bits. So no matter where you think it was going to land in your layout of your struct, where it lands will be a multiple of 8 bytes. Because its natural alignment is 8. All right, so I wish I could put in a question mark, but I can't. All right, so now I just put in a char tucked in after the first integer. So let's get and let's see what this does. Where do you think it's going to be? What do you think it'll do to the size of the struct?
I don't think it will change because there's memory between in second int and node star. So they're just gonna chuck char hum between there.
Yeah, Cephas is correct. The size of the node did not change. And notice that the offset of is 4. It's coming immediately behind, immediately after second int. And the size of the struct didn't change.
So basically it adds like a little buffer just in case you.
No, there's no just in case. The idea is, let's draw this out. Good. All right, so here's our new struct. So here's our, and this is 8 bytes. Okay, so we have second int, which is only 4 bytes long. Then we also saw that next started on an 8-byte boundary, right? And then we had payload. And that is only 4 bytes. And we saw that the size of this was 8 plus 8 plus 8, or 24 bytes. Okay. And then we added, and where did it go? It went here. Okay, so now we have 3 bytes unused. Well, I'll tell you what, let's do something straightforward. Let's add a short after, huh? Let's add a short after this and see what happens. Okay. Now, do you think that the size of the struct will change? Anybody?
I think it will not, because a short is a size of 2, right?
Yeah, where do you think its offset will be then? So you're right, the size of this full struct shouldn't change, but what do you think its offset's going to be?
6. Or
Let's see, so
4.
for
No.
you got, well, I'm trying to work it out with you, so I think you
Yes.
might be right. So 4 for second int, then 5 would be a length of getting it to huh. So 6 bytes, but that address isn't really 6, it's 5, right? Because we counted 0. You start counting at 0. So anyway, let's find out. So what did I do? I put in Hausa, and now let's find out.
So when we internally add something onto the stack, whatever the actual assembly code written is going to start on a memory address that's divisible by 16.
Stevens, I'm going to apologize to you because I was thinking about something else when you started your comment, and I'm sorry, I missed it. Could you say it again?
So internally, when this is compiled down to like assembly, when we say node n, it's going to be added onto a stack on a memory address divisible by 16, just like in normal assembly.
That's a really interesting question. Maybe we should look at, oh, but this is on Intel. So let me quick transfer this over back to the ARM machine, and let's take a look at the actual code. Okay, let me paste now. Okay, so now I'm back on the ARM machine. Let's take a look at how the stack is manipulated. Let's see, so G++, and let's turn on the optimizer so we have less code to look at, and -S of alignment.cpp, that'll blow up the other one. Okay. So let's see, we've got alignment.s should be that code. Okay. Look at that. A movement of the stack by 64 bytes. Isn't that interesting? And, oh, what's this? Oh, screw that. Let's just stay here and try to explain that. So you've got 16 needed to store X29 and X30, yet there's 48 more bytes. Now the size of this one is 24. So let's see. I'm writing something down, and so we've got 16 plus 24, and that is going to be 40. But is 40 a multiple of 16? So what's the next higher multiple of 16?
32.
The
So
next one.
Next higher than 40.
48.
Okay. So there's something else going on the stack, but I would have all things being equal, if I were writing this as a human assembly language programmer, the 64 on this line would be a 48. So even though it's a little different than what I would have expected, I will attribute that to going through the C++ compiler instead of hand coding it. But it still answers Cephas's question. Go ahead. Go ahead, Cephas.
So what if, because if we have that 48, there's plus the 16 to save the stack and frame pointers, which 48 plus the extra 16 that those take up is 64.
I know that.
Is that what they're
no, but-
doing? You went out. I can't hear anything.
Yeah, I was whispering. So it's 16 for the x29 and 30, but then we also have a local variable called that's the struct, and that's 24 bytes. So that's why I did 16 plus 24. So that sums to 40. 40 is no good, so it should be summing to 48 to be a multiple of 16. But for some reason, the compiler added another 16 on top of that.
Yeah, but you have to save the stack and frame pointers.
I did.
No, that's what I'm
What?
saying. What if this 64 includes everything they're going to put on the stack?
Right, I'm enumerating for you the things that I know are on the stack now. There are
Oh, so you
16
included.
bytes.
Okay, never mind.
Right,
I get it.
right. Okay. All right, so there's an extra 16 here. But I attribute that to the compiler being less efficient than I would be if I was writing this myself. Okay. We're back here. So did it change the size of the struct by adding that short? No. But even though it could have started at address, looking down here, even though you might think that Hausa starts at 5 units away because we got 4 for an int and 1 for a char, it didn't start at 5. So 0, 1, 2, 3, 4, 5. It didn't start there. It started at 6 because the natural alignment of a short is even addresses. Okay. So when you are thinking about creating a struct, this is for your higher level language. When you create a struct, always think about what the alignment of the individual components of the struct are, and are you ordering them in such a way that you'll cause waste of space? Okay? Because it's very easy, and I showed you, just by changing the order, you get internal fragmentation, internal wasted space. Okay? Okay, any questions about the way structs get laid out? Okay. So let's just do it. So was there any questions? I'm looking at people's faces. Neto, how you doing? Just a thumbs up. You don't have to unmute. Okay. And Gabe, how you doing? And Jacob, you're taking notes, not sleeping. Right. Okay. Good. Yeah, I saw your head over like this, but I assumed you were taking notes. All right, Michael. Good. I see a bit of a thumb. All right. Let's take a look. I'm taking a look at the, so we've talked about size of. So if you're ever curious how big a struct is, use size of. Size of will never lie. Okay?
How do we do something like size of in ARM?
You don't.
Fair enough.
Yeah.
That's basically.
So-
how I wrote, yeah.
Right, so you don't. In fact, nowhere in your assembly language is there a struct. There's no syntax for a struct. So in order to make use of a struct, you have to document where the offset of everything is. And if necessary, if it becomes difficult for you, write a program just like this one. And it'll tell you where everything really is. Keep in mind that if you're using a struct or the equivalent of a struct from assembly language, that if your data structure changes, all of your offsets are going to change. Okay? Okay. So we've done 3 of the things on the list of things to do today. So we've done struct layout, alignment, and size up. Okay. All right.
No bueno.
No good?
No, it's fine. Ignore me.
Okay. Uh, okay, well, I blew away. Let me go get a program to work with the next set of things to learn. Okay, so. All right, so I've got some code here that I'm showing. And I want you to comment it for me. So let's comment main. So what is line 14 doing?
We increment whatever is in x1.
Whatever is in X1. What's in X1?
argv, something
That's
you passed to
correct.
argv.
Yes, so skip over. Hey, wait. You're supposed to be doing this, class. So what am I skipping over?
The name of the
You're skipping
program.
over a dot out.
Or what you mean by that is argv sub 0. Right?
Okay.
Yes.
Yeah, good. What is the purpose of line 15?
Loading argv1 into x0.
Loading all of argv1 into x0, that's a pretty cool trick. Are you sure about that? Let's be very precise.
Loading.
Address of argv into x0.
You're dereferencing the char array, the first element in the char array that argv1 points to.
Okay, good one. What is the purpose of line 16? And somebody else this time.
It's checking to see if x0 is 0 or null, and if it is, it branches to 1.
Okay, is that a fair comment?
Yes.
Okay. And what's this?
You are going to use what, if that is true, you're going to do this next line. So you're going to branch to this next function that you've got called attoy.
Okay, and that is A to I.
It converts a string, a char
Oh.
array, to an integer.
So Paul, this is calling A to I with argv1. Okay, so ASCII to integer. Right, because the command line arguments are all strings, but I want it to be a number. Okay, and then Paul print with an integer, an int. So we don't know, that's all we know about print right now. Let's take a look at this code then. So help me write the documents for this. What is the purpose, what is line 6 doing?
It is putting whatever is in W0 into W1.
Yes, I can read. What is it doing?
Takes
That's
the
like-
first parameter and puts it in W1.
Yeah, so Thomas, that comment that you gave is like writing a comment in your C code for C I++, and you write the comment increment I. I know, I can read it,
There.
right?
Mhm.
So this is, the way that this is called is an int. So why do I have, so Cephas, can you repeat?
It stores the first parameter in W1 to do something else with it, I guess. I'm not sure yet.
Okay, so whoops.
So why stored in W1? Ah,
Well-
never mind. You have to do it printf. I get it.
Yes, that's right. So FMT will go in, you should be writing this, not me. Right? And what is the purpose of this? To get the real purpose of that, you should look down here at the format string. So I'm going to print the same int twice, once as decimal and once as hexadecimal. Okay?
Okay.
All right. So things froze on me, sorry. All right. So what is this, the purpose of this line?
Making the address of x0 equal to FMT so it can be printed using printf.
Okay, good, good. Let's call that load address of FMT. And this obviously is the call to printf. Okay, good. So we've written documentation for this. Let me hit save. And now it's on my ARM machine. Let me make sure it's here. Yep. So GCC test.s. Let's test it out. No command arguments, does nothing. But let's take a look at this. A.out, and I'll give it a 1.
We still see your Visual Studio code. We're not seeing what you're doing on the ARM machine.
Thank you. Just once, I'd like to get through a whole class without making that mistake. Okay, so A.out by itself.
We would
the program.
too.
Yeah, thank you. Shut up. So A.out by itself is just ends. A.out with a 1. So the decimal 1 in hexadecimal is 1. All right, now let's introduce hexadecimal. No computer organization course is complete without understanding hex. So what is decimal? Decimal has a ones place. To the left of it is a tens place. And to the left of it is a hundreds place, et cetera, et cetera. True? Okay.
Yes, I agree.
Now in hexadecimal, we have a ones place, a 16s place, and a 256 place. And that is up here, that is 10 to the 0, 10 to the 1, 10 to the 2. 1, 10, 100. Now down here, you've got 16 to the 0, 16 to the 1, and 16 squared. And of course, it continues. More digits follows the same set of rules. Okay. Now, each of those places has to have some digit associated with them. And all we know about is 0 through 9 in Arabic numerals. Right? So how do I encode the numbers in hexadecimal greater than 10? 10 or greater, I should say, because we only have 0 to 9. So A is 10, and B will be 11, and C will be 12, and D will be 13, and E will be 14, and F will be 15. So now we have an alphabet to encode 16 different values. So 0 through 9, A, B, C, D, E, F. So why hexadecimal? Because Apple, no, kidding. Because it is a convenient shorthand for binary. Okay? So let me ask you a question. What exponent applied to 2 equals 16? Correct. Jordan is correct. 4. So every hexadecimal digit corresponds to 4 binary digits. So if I wanted to write 255 in binary, I'd have to write 8 consecutive ones. Or in hexadecimal, I can write FF. So hex FF is binary 1, 1, 1, 1, 1, 1, 1, 1. Maybe I got the number ones wrong, but it's decimal 255. Okay, so this is why hex is used so frequently. Okay, any questions?
Base 10 is definitely easier though. Just saying.
What about octals?
Yeah. Okay. So octal is also very commonly used. So octal is base 8. So there's the ones place, the eights place, and the 64s place. And that would be 8 to the 0, 8 to the 1, 8 to the square. Now you can write octal in C and C++. Have you ever done that?
No.
Okay. Well, what are the digits in octal?
1 to 8 was 0, I guess 0 to 7.
0 to 7, right. So how you use this in a high-level language is C and C++.
Like 0.
That's 100. That's 123. Leading 0 turns it into octal. Okay. All right. So yes, octal does exist, but it's nowhere near as natural for representing binary, because in 1 byte, how many hex digits are there? 2. In 1 byte, how many bits does it take to represent 1 byte in octal? Well, octal is 3 bits at a time. 3 bits at a time. So 3, 6, 9. Okay, well then it takes 3 digits in octal to represent the byte, where the most significant digit would always be a 1. If you're doing 255, sorry.
So why do we represent hexadecimals, octals, or just hexadecimals in general from right to left instead of left to right?
Oh, okay. And you know what? That's actually a huge question. That's a much bigger question than I think you meant to ask. And that has to do with endiness. Okay. So there's in Gulliver's Travels, there's a war fought between Lilliput and Blefuscu. And the basis of the war between Lilliput and Blefuscu is when you're having an egg, which end do you crack it on? Do you crack it on the little end or the big end? So how that carries over into computer science is the order of the bytes in a primitive data type that is more than 1 byte. So char, there's only one way to represent a char. But if you had a short or an int, what are the order of the bytes? And it turns out some computers are little endian and some computers are big endian. So on some computers, you might have, let's say it was a short, you might have the first byte and the second byte, and that makes a short. But on other computers, it actually might look like this. The second byte comes first at the lower memory address, and then the first byte. And these are the same short, just on different computers. Okay, so what endiness is the ARM? Jordan is seeking the answer in Google, right? Go ahead.
I had my, I'm not Google. You want me to Google it?
ARM
Yeah, I want
is
you all-
technically both. At least ARM, the one we're using.
Yeah,
ARM
well,
is little endian by default, but can be programmed to operate as big endian. Many older processors were big endian, such as the Motorola M68K and the Spark.
Okay, so the ARM is both, but by default it's little endian. Okay, and what is
So-
the x86?
Let me get this straight. So little endian means you have the most significant digit is first. It's at the end of the, if you're reading from left to right, I guess it's at the end. Is that what's up, or is that the opposite? I always got these confused, and I never liked them very
Yeah.
much.
Right. So I think we all would agree that Cephas is a pretty capable CS student. And what he's saying is he always gets confused and he never knows which is which, and yet he's extremely capable. So the lesson here is, for most of the time, most of us, who cares? Okay, now where this gets really in your face is in networking. Because writing something to a network serializes the bits. The bits have to go out in a certain order. So when you transmit an int to another computer on the network, if that computer is not programmed correctly and your code is not programmed correctly, and one is big endian and one is little endian, you're actually not going to be able to communicate. Okay, so for the purposes of this course, the cool thing to know, the knowledge, is that little endian and big endian exist and they're different. If
Not
you start
particularly
doing,
useful.
well, but if you start doing any network programming, that knowledge becomes critical.
Honestly, we should just settle and move on with life. Why keep this up?
I don't know, you got me. Because, all right, so that's endian and that's hexadecimal. Let's go back to the program here. Because let's learn what it is that I wanted to teach, which included hexadecimal. But let's put in -1. What's the hex for -1 do you expect? So what the heck is that?
Is that the byte value just before? I don't know. I thought I knew, but no idea.
It's
Okay.
2's complement.
All right, well, you introduced the term, Cephas. What does it mean?
It's the way that signed integers are commonly stored in memory.
Okay, good, that's fair. So let's talk about signed. What does it mean to be signed or unsigned? So here's a byte, and it has 8 places in it because it's 1 byte.
We are still looking at the other
Yep,
one.
thank you. Yeah. So let's do a shorthand. Just say that I'm, projecting wrong or whatever. Okay, so here's a byte. And here are the bit numbers. This is little endian. 4, 5, 6, 7. Okay, so before I demonstrated that here's 1 hex digit and here is another hex digit. All right, and what is it that I was trying, what was the point that I was trying to make? Oh, yes. So when a value, a primitive type is assigned primitive type, like int, short, long, etc., the most significant bit, the highest numbered bit, is the sign bit. So if the most significant bit is a 1, then the number is negative. If the most significant bit is a 0, then the number is positive. Well, that seems clear enough. So it makes sense that if 1 is this, then -1 ought to be this. right? According to my definition of sign. Okay. But we don't store negative integers this way. And there's a reason for that. Does anybody want to consult Google and find out, tell me why? Why don't we store negative numbers just using the sign bit?
Honestly, I should know this, but I definitely forgot.
Okay, well, tell you what. Let's look at the numbers for, is 0 this? Or is it this? Which one is it? Well, it's either 0 or negative 0, which is also 0. So because you can have 2 values for 0, we don't use this method. Instead, we use something called 2's complement. Okay? And what 2's complement is invert all the bits and then add 1. Okay, so that's how you get both into 2's complement and out of 2's complement. By the way, this is the reason why this lesson is coming now, is it'll help you understand detecting negative numbers, right, in project 2.
What does it mean to invert all the bits?
Excellent question. So let's take our value of 1. So 1, 2, 3, 4, 1, 2, 3, 1. Now, inverting all the bits would give you 1, 1, 1, 1, 1, 1, 1, 0. So if it's a 0, make it a 1. If it's a 1, make it a 0. And now add 1. What do you get? 1, 1, 1, 1, 1, 1, 1, 1, or negative 1.
So how does the computer know to interpret that as -1 instead of I'm not going to do the binary in my head right now, but
Yeah, okay.
instead of it being a large positive
That
number?
would be
wait,
255.
the overflow though, right? It wouldn't know.
Well, overflow works in here somewhere, but how does the computer know is your question. The answer is, it doesn't. Do you know who knows?
The programmer and convention.
Yeah, you know, right? And you're the one who either writes int foo or unsigned int foo. And then you depend upon the compiler to take care of the rest. Okay? So part of the beauty of 2's complement is the computer doesn't have to know, because watch what happens when you add, what should you get if you add -1 and 1?
0.
All right, so let's add 1 here. Okay, so 1 plus 1 is 0 with a carry, which is a 0 with a carry, which is 0 with a carry, with a 0 with a carry, with a 0 with a carry. Okay, and it turns out there is a carry out called overflow. Okay. But you see how just adding the 2's complement of -1 to +1, I get 0. So the logic, the hardware logic that does addition on positive numbers and subtraction and multiplication, etc., works the same. It's the same hardware to work with 2's complement.
I actually implemented the ALU to do this in hardware, whatever you call it, hardware code. I don't remember.
Well, I don't know what it is that you're doing. So you mean in like VHDL?
Yeah, that one, VHDL.
Ah, boy, it's like I'm so smart. Okay. Okay, do we have any questions about what it means to be a signed versus unsigned integer? In theory.
Isn't the unsigned the one that is the inverted one? Or is it the other way around?
No, the unsigned means that there is no sign bit. So let's take a look at an int, well, a char. A char that had the value of 1, 1, 1, 1, 1, 1, 1, 1, that's -1. But an unsigned char with the same bits is 255. Okay. So signed versus unsigned means, are you reserving the topmost, the most significant bit as the bit that determines the sign of the number? If you're not reserving it, then it's an unsigned number. Okay. Have you
Okay.
ever written, I'm sorry, Rebecca, did I answer your question?
Yeah, you did.
Okay, so have you ever written an infinite loop when you were trying to do like a for loop where you were decrementing? So for unsigned int I is equal to 100, while I is greater than or equal to 0, I minus minus. You're trying to write a loop that decrements instead of increments. What I just wrote is an infinite loop. Why? This loop will stop when I is negative, but if I is an unsigned int, then there are no negatives. That's why this is an infinite loop.
Wait, but shouldn't it break when I is? No, I get it. Never mind.
Okay. All right, now, depending upon what your intent was in the higher level language, the compiler will generate all the right instructions. If it was intended to be signed, it'll generate signed instructions. If it's unsigned, it'll do something different, okay? But in assembly language, when you need to switch, when you need to do casting of, let's say, if you have char A and you have int B, both of these are signed. So if you wanted to, if cast A to match B, it would be something like int A, and you put that in B. Now, of course, I know that there's promotion between the integer types, but technically this is what's happening under the hood. Okay. But if it's unsigned, you actually have to use different instruction to do that cast in assembly language. So there'll be a sign extended or zero filled.
Didn't we
So-
talk
so-
about this in the ARM reference manual?
Yes, we did. And thank you so much, Nate, for remembering. Good on you. Okay. Thank you. So to complete that sentence, what would be the difference? What would it look like to be the difference between a zero extended or sign extended? Well, let's suppose we had FF and 00000. All right, so that's a 32-bit 255, right? Now let's say you want to cast this to an integer. All right, what do you do with the, well, you know, let me actually, I'm going to change that and give you a much better example. So let's say you wanted to convert a value in a W register to an X register. You want to go from something which is a byte short or int up to a long. There is actually a correct way to do it. And that is, if it's unsigned, use the unsigned promotion instruction, which is zero filled. But if the W register is signed, then you use a different instruction. So let me write it out. So if it's unsigned, and you went from 1 and you use the unsigned extension, you'll get zeros all the way up. Okay. But if this was a signed extension, let's say it was FF, so that's -1. The proper way to promote this char to a bigger integer is you got to write F's all the way, not zeros. So that's what it means to be sign extended. Okay. At this point, let's reserve 10 minutes for talking about the project. Can I have your questions, please?
Can you show us an example of implementing the struct as a global variable in ARM?
Sure. I think I can do that. So let's go here. And I'll go back here. Okay, so we're in the data area. And remember, I created a node named N. So to make it a global variable, you would say N dot space, and you'd say 16. And just to make sure, fill it with zeros.
Isn't there 2 variables in there? So we'd put two zeros.
No, see, the assembly language doesn't know that this is a struct. All that the assembly language is aware of is that it takes up 16 bytes.
All right.
Okay, another question? Okay, so there are comments, which I haven't seen, so. Upload what to GitHub?
the alignment code that you had, and then when we translated it to assembly? If you want, you don't have to.
I think I did that. Let me look. I think I've already done that. Let's go here. And yeah, I'll let you see what I'm doing. So this is the GitHub page. And do while function calls, if statements. I thought I had something. I thought I did. Okay, I'll write a program for you. But I'm sure I have it somewhere, but rather than go find it, I'll write a new one. Okay, so the negative program that we just commented, let's go back to the negative numbers. And, oh, well, this is still here. So I'll put this up and tell you the link. Okay, and git push. Let me get you the link. Where am I going? I need a browser. All right, and I need GitHub. Okay, here comes the link. I'm pretty sure this is public. Oh yeah, and there's something really cool here. And we have 5 minutes left. Cool. So let me give you the link. There's the chat. Chitty chat. There is the chat. Okay, can somebody click on that and confirm you can get there? Because it might be private. It should be public.
I can.
Okay. All right, now there's something on that README that's really cool. So let me demonstrate it. And this may help you debug. Let's see. GCC, just make sure I know what I've got. That won't matter. Whoops. What just happened? Oh, I'm on the wrong computer. Darn. Okay. GCC-03 test status. Okay. So check out this command, objdump-d /a.out.
You need to switch.
It's hard. It's really hard to keep track. That's why you need a producer. Okay, there you are. Ready? Okay, check it out. There is your code. And here are the addresses of your instructions. And here are the opcodes. Remember we talked about opcodes? And I draw your attention to these two lines. Look at that. They are the same instruction. They're both moves, and they're both W0s, but into a different destination. And you see that the destination is encoded in the instruction. Okay? Okay, cool. and you can disassemble other people's code. So let's see, /bin. What's in /bin? All right, there's a program called less in /bin. So obj dump -d /bin /less. Okay. So if you want to reverse engineer somebody, sure, you can get at the assembly language, no problem.
That cannot be fun.
I've done it. So you may have to do it too someday.
I mean, that would be really difficult to do.
Fun. Okay. All right. Any questions about that? Questions about your project? We have a minute. Less than a minute.
Wait, so conceivably, if we could get access to your files, we could just object dump it and steal the assembly code and
Yeah,
done
but
with
then
it.
you'd be booted out of this class for plagiarism.
Not if he doesn't find out.
I think he'd be able to see the fact that you copied his code.
He would be able to tell.
And now you could just
I would look
sneakily
at your
SSH into his computer.
Yeah. Well, two
SCP.
things.
Boom, gone.
Two things for that is one, I would remark how wonderful a coder you are in assembly language, and two, this actually did happen once while I was here at Carthage, and the student, of course, I identified it immediately without trouble, and it was in a day, back in the day, we didn't have the ARM emulators, so we used actual tiny little ARM machines, like Raspberry Pis. So what the student didn't know is that everything that you do on those machines was recorded. So when I went to the provost in order to fail this student and cause them to go into the academic dishonesty process, I was actually also able to show them their keystrokes demonstrating how they were trying to get my code. So anyway,
Fun.
that was.
I'll just have to be better than him. Or her.
Yeah.
Quick question.
Yeah, fast.
So we did that thing inside our code to stop the randomization, the space randomization. Is that why in your example code for P2, all of the addresses are so close together and it reuses the same addresses depending on how the numbers are input?
Kind of. So with address space randomization turned off, the first node will, no matter how many times you run the program, the nodes will land in the same addresses. If address space randomization is still turned on, then don't be surprised. In fact, you can expect that each of your mallocs will, from invocation to invocation, be different. However, the way that malloc works and the allocation works is that if you were to malloc two nodes, they would be consecutive.
Okay.
You know, malloc, and you'll get actually consecutive bytes. Okay. All right, so it is 2 minutes post class. I just want to say I'm very happy with the way the class is going. I'm hoping that you are happy as well. There are some students in the class that I would like to hear more from. Okay, so if you're not someone who speaks up, then you really got to start thinking about speaking up. Okay.
I'm glad that I asked some good questions.
Yep. Okay.
Like, how do you do an and?
Okay, we did that earlier in class, so I'm not going to do it again. I know. It was
Yeah, I know.
rhetorical, kidding.
I'm just mentioning
I'm
that.
kidding.
Was like, yeah.
Yeah, I'm just yanking your chain. I'd like to wish you a wonderful weekend. Reach out to me. There is a barbecue tonight, 7 to 9 p.m. on Discord, and have a good weekend.